this part of this section 2.6, it talks about Ricardi differential equations. Ricardi differential equations. What are Ricardi differential equations? Those are the equations written in the form dy dx equals p of x plus q of xy plus r of x y squared. It's kind of like a quadratic form. Looks like quadratic form on the right side and differential on the left side. Those kind of equations can be solved using y equals y1 plus u, whereas y1 is a given or known particular solution. This will be given to us. And this will help us, this trick will help us to build the general solution for the differential equation. So this y is the general solution for this kind of differential equations. So from this y equals y1 plus u, if we differentiate both sides with respect to x, we get dy dx is dy1 dx plus du dx. And what I'm going to do is substitute this into this equation. Dy dx is dy1 dx plus du dx equals p of x, I'm just going to write p for now, plus q times y is y1 plus u. I'm substituting r of x, I'm just going to write r y1 plus u squared. Let's keep the left hand side the same for now. Keep this the same. Multiply this out. qy1 plus qu plus r y1 squared 2r y1u plus ru squared. Let's keep the left hand side the same. For this one, I'm gonna group the p or p of x, so p or p of x together with q y1. So I'm gonna group this, and this one, ry1 squared together. And now I'm gonna factor among these two the u, and that will leave ru squared. So notice, what is this here? That's like p of x, q of x y1, r of x y1 squared. That's exactly the same one that I started my equation with, the right hand side. That's dy dx. But the only difference, instead of y, I have y1. So I can keep the left hand side the same for now. I can replace this with dy1 dx plus q plus 2r y1 u plus ru squared. These cancel each other. And that gives me du dx. I can subtract that part to the left hand side. U equals ru squared. Now, this is what? What kind of equation is this now? This is, which is a Bernoulli differential equation. So this guy was able to transform that kind of differential equations into Bernoulli. And then from there, you can use what we just learned in the first part of this section, how to solve Bernoulli differential equations. So the trick is you take W to be, in this case, it's a, instead of Y to the 1 minus N, there's a U here to 1 minus N. And notice what N is. N is 2. This is N. So that would be U to the 1 minus 2. That's U to the negative 1. So then differentiating both sides with respect to x, dw dx is negative u to the negative 2 du dx. Solve for du dx. That gives us negative u square dw dx if you divide both sides by u to the negative 2. So this is just a process about how to solve this kind of equations. Now, after we got this, we're going to substitute this back in there. The du dx can be replaced with negative u square dw dx minus, keep this the same, 2ry1. Instead of u is just keep u for now. We need things in terms of u. And then ru square. Divide everything by negative u square, this one. That gives us w dx, dw dx, plus q plus 2ry1, u to the negative 1, equals negative r. But notice I have dw, so I expect this to be in terms of w. Well, what is that? This is from here, u to the negative 1 is really w. So you can replace that with w. And now this process, the Bernoulli process, transformed that differential equation into linear. So we can say which is a linear differential equation that can be solved easily. And to see how this can be applied, let's look at an example. Let's say we're asked to solve dy dx equals negative 4 over x squared minus 1 over xy plus y squared with a given particular solution y1 equals 2 over x. This is, as you can see, this is a Ricardi differential equation. So it says we proved earlier that the Ricardi differential equation that I started with, this one, we were able to transform it into an equation in this form that I'm going to highlight, this form. dw dx plus q. Where is q here? This is p of x. This is q of x. This is r of x. So q of x is negative 1 over x plus 2. R is R is 1. And y1, what is y1 here? It's given 2 over x. W equals negative r. Everything looks good. So dw dx, this is 4 over x minus 1 over x, 3 over x. W is negative 1. This is linear differential equation. We use the integrating factor I of x equals e the integral of p of x dx, like so, e 3 integral 1 over x dx, e 3 natural log of x, move the 3 up, and e ln of anything is the thing itself. After we got that, if you remember, d dx of the integrating factor x cubed times w is equal to what? Negative x cubed. Integrating both sides, x cubed w is negative x to the fourth over 4 plus c. So what are you trying to find here? Well, let me go back up. We said that this kind of differential equations has a solution in this format. Y equals y1 plus u. Well, y1 is given. They give it to us. We just need to find the u. That's why we can go back and remember w is u to the negative 1. That's what w is. W is u to the negative 1. So I'm going to replace w with u to the negative 1 because I need to solve for u. Divide everything by x cubed, so that's negative x over 4 plus cx to the negative 3. 1 over u equals negative x over 4 plus cx to the negative 3. If I want to find u, I just flip both sides, 1 over that. Then, after we found the u, the y is always y1 plus u. Y1, they give it to us 2 over x, and u is what we just found. That's the general solution. So the procedure here, how this worked, is that we took the Ricardi differential equation, we transformed it into Bernoulli differential equation, and from there we used Bernoulli and transformed that into linear. And then after we were able to transform to linear, we could use the integrating factor to solve for that linear differential equation. Plus the trick that we have here, that y, the general solution y equals y1 plus u. Move on now. we have the last one is Clairaut differential equations. Those are the equations in the form y equals xy prime plus f of y prime. F of y prime. So that looks like y equals x times the derivative of y plus a function evaluated or calculated at the derivative of y. So what happens, this kind of differential equation has solutions in the form of y equals cx plus f of c of x plus f of c. What are these things? C is a constant here, so f of c would be a constant as well. So this y equals c of x plus f of c is basically a family of lines, right? Like for every c value you will be getting a straight line. So these straight lines will satisfy the equation, the given differential equation. And you can actually verify why this works for that given differential equation by finding y prime, which is simply c at times 1 plus 0, so that's c. And if you put it back in there, what are you going to get if you put this back into this? You're going to get y equals x times y prime is c plus f of y prime is c. So that gives us this one. It matches. That's just to verify it. On the top of this, this solution that we got there, that's a general solution to that given differential equation. So this kind of differential equations may possess a singular solution. In the form of parametric stuff, which is given by x equals f prime of t and y equals f of t minus t f prime of t, provided that the second derivative at t is never 0. And to see how this works, we can look at this example from the textbook to solve xy prime plus 1/2 y prime square. To do that, we first need to find what is f of y prime, because if you look back, it was xy prime plus, so it looks like xy prime plus f prime of f of y prime. If you compare it to this, that tells you f of y prime is 1/2 y prime square. So what is the solution? We told you that the general solution is cx plus f of c. Well, cx, nothing can be done. F of c, so from here you can find f of c by replacing y prime with c, so you get 1/2 c squared. So that would be the solution. Note from f of y prime is equals to 1/2 y prime square, we can find f of t. F of t is 1/2 t square if you replace y prime with t. Notice something, if you find the derivative of this, that would give us t, and the second derivative is simply 1, which is not 0. So this confirms there is a singular solution. there is a singular solution. And how do you find that singular solution? Well, we give you the formula negative f prime of t, which we found to be t, and y is f of t minus t f prime of t, which is negative 1/2 t squared. Now what you can do from this one, you can solve for t, which is negative x, and substitute it in there. You get negative 1/2 negative x squared. So y is negative 1/2 x squared. Do you see this is, this solution also works. So this means graphically, if you like to graph this, maybe the graph, that one looks like this. Y equals negative 1/2 x squared. And for the one we found, y equals cx plus 1/2 c squared. For every c value you choose here, you get a solution. So if you choose c to be 1, so that would give us x plus 1/2. If you choose c to be negative 1, you get negative x plus 1/2, and so on and so forth. So for every c value, there is a solution to the given differential equation.